the valence bond theory of hybridization. One of the issues that arises is that the number of partially filled or completely empty atomic orbitals did not predict the number of bonds or the orientation of bonds. Carbon is a prime example. Carbon, with its 2s2, 2p1, 2p1, 2p0, would predict 2 of the 3 bonds that are 90 degrees apart rather than 4 bonds that are 109.5 apart. Therefore, we are going to hybridize. I'm going to clarify with a simple example of this particular slide. Carbon lives in group 4A. When we draw a Lewis dot structure for carbon, we were taught to draw one top, bottom, left, right. 4 dots, one around each side, before you go back and give partners. What we were actually showing you is something quite advanced. It's called a hybrid orbital. Let me explain with our electron configuration. Carbon is number 6. I looked at my chart, number 6. To represent 6 electrons using our electron configuration, we would write that as 1s2, 2s2, 2p2, giving me 246 total number of electrons. And if we represent that using the orbital diagrams, either with boxes or circles or dashed lines, we would place 2 electrons in the first energy level, 2 more electrons in the second energy level, 2s2. The p have 3 different orientations. We called them px, py, pz, and we would place 2 electrons in the second sublevel of the second energy level. But what we notice is we have a completely empty orbital in the p sublevel and a filled sublevel in the s. Recognizing that it's one electron pair that needs a partner, I would suspect that only 2 bonds would form with carbon, and yet that's clearly not the observed pattern of bonding. What we do instead, and it really is just automatically what we've done up here, we promote 1 electron from the s orbital and let it have its own room, and we hybridized an orbital. Hybrid means a combination of 2 things. So truly what we're showing is 1 electron in the s sublevel and 3 electrons in the p sublevel, creating 4 open spots for bonding. By promoting a paired electron to an empty orbital, we've created 4 open spots. And that's exactly when we draw 4 dots around carbon, we're ready to create 4 bonds. So intuitively, we already knew carbon had 4 bonds, but yet according to its electron configuration, we wouldn't readily see that unless we promoted to the empty orbital. Why would we want to partner in the same room, if you will, when there's an empty room down the hall? Everybody take their own room and spread out. That's really all that term means, to create a hybrid orbital. Carbon is a great example simply because it pairs the first 2 and leaves an empty orbital. Instead, we promote the 1 into the empty orbital, creating 4 open spots for bonding. That really is what this slide is trying to tell us. If carbon is a mix of all the s's and p orbitals to get 4 orbitals at the point of the corners of a tetrahedron, I'm creating 4 spots for bonding by promoting a paired set of electrons into an empty orbital. Now I see 4 spots open for bonding business. Alrighty. That's what this slide is showing. If hydrogen is a 1s orbital, carbon would be written as 2s2, 2p2. I would predict only 2 spots for bonding and leaving an empty orbital. But carbon clearly has 4 spots open for bonding. So instead, we simply promote, and that's what this slide was showing us. We promote this electron here into the empty orbital. I keep grabbing a pen with no ink. Promote that one, unpair it and promote it to the p orbital. And we come up with the boxes as we drew a moment ago, where I have 2s1, 2p3, 4 open spots for bonding. So the observed reality with 4 spots, different than the theoretical prediction if I left it as a partnered pair. Hybridization. To promote electrons into an energy level by unpartnering. So the valence bond theory, I need to check, am I on the right slide? Yep, 77. The valence bond theory has some main concepts, and let's share what those are. It says the valence electrons of the atom in a molecule reside in the quantum mechanical atomic orbitals. That's fancy for saying the S, which are spherical, the P, which are hourglass shaped, the D, which stands for diffuse, if you remember they look like clover leaves, and the F orbitals, or they may hybridize to be any kind of combination thereof. A chemical bond that results when these atomic orbitals interact, and there is a total of 2 electrons in the new molecular orbital, and they must spin in opposite directions, so the spin is the same rule. One spins up, the other will spin down. The shape of the molecule is determined by the geometry of the interacting orbitals. Some atoms hybridize their orbitals to maximize their bonding, as in our carbon example. If I can create more bonds by promoting into empty orbitals, an atom will do that. It creates stability. Hybridizing is simply mixing different types of orbitals in the valence shell to make new sets of degenerate orbitals. As in what we did here, we promoted an S electron into a P orbital. By promoting it, we created a combination of an sp hybrid orbital. If an S is spherical and a P is an hourglass, not bad for my drawing, and I take these 2 pictures and literally combine them into one, I get a combination of an hourglass and a sphere-shaped orbital. Not quite an S, not quite a P, it's between the 2. And that's what the term hybrid means, a combination between the 2 orbitals. We created, with that carbon example, a hybrid orbital known as an sp. It is between an S in energy level and the P in energy levels. So the same type of atom can have many different types of hybridization. Carbon, sp, sp2, or sp3 hybridization. sp1, p2, or p3 hybridization. Each one of those can be hybridized. So hybrid orbitals, the number of standard atomic orbitals combined, creating the number of hybrid orbitals formed. So combining a 2s with a 2p gives 2sp hybrid orbitals. On a note, hydrogen cannot hybridize. It's simply the smallest atom and can't be promoted because it only has a 1s shell. And it only has 1 orbital. There's nothing to promote it into. The number and types of standard atomic orbitals combined determines the shape of the hybrid orbital. And that particular kind of hybridization that occurs is the one that yields the lowest overall energy for the molecule. This sounds complicated, but it truly isn't. It really isn't. Let's just take some examples. Carbon, in its unhybridized, what we would normally consider writing out 1s2, 2s2, 2p2, but I have an empty orbital. So I want to take this electron, unpair it, and promote it to this orbital here. What would we have left? We would have a hybridized orbital where I promoted this electron here. The 2p orbital, or still this guy, those are still the same. But I'm going to take this s orbital and I'm going to combine it with this empty orbital. And when I promote this electron, I create 2 of equal energy hybrid orbitals. This becomes an sp orbital, and this becomes an sp orbital. The 2s orbital no longer exists. If this is 2px, 2py, 2pz, think about this one still being the 2x, 2y, and the z no longer exists. These 2 become of equal energy. They're called sp hybrids. The 2 electrons that were originally in the p are still left alone. When I hybridize, promoting an electron into an empty orbital, these 2 now are of equal energy. They're not an s, they're not a p. They've been combined to be an sp orbital. Suppose an sp2 hybridized orbital. I can see 3 of equal energy, 1 left in a p sublevel. And sp3 hybridized. sp3 creates 1, 2, 3, 4 of equal energy levels. When we begin bonding, it's really simple, and I just call it my finger-thumb rule. If I want to know how many electron or what is the hybridized orbital, I count. And I always start with my thumb as number 1 because that's just what I've done. Find the central atom, it's carbon. How many electron domains? 1, 2. 2 electron domains. Your thumb is always the S. Draw an S on your thumb. I just did. 2 electron domains. Thumb first always. One of them will always be an S. To get two fingers in the air, a thumb and a finger, to get 2 electron domains, sp hybridization. sp, 2 fingers in the air. Down here, 3 electron domains. Carbon in the center, 1, 2, 3 electron domains. Thumb first, sp2. S is my thumb, always, always. To get 3 electron domains, I got to put 2 more fingers in the air. sp2, hybridization. Here's carbon. 1, 2, 3, 4 electron domains. What would be the hybridization? Finger-thumb rule. Start with your thumb, it's the S. Always put the thumb up first. I need to get to 4. 1, 2, 3 more fingers in the air to get a total of 4 electron domains, sp3. Your thumb first gets the electron domain for the first one. If I need 2 total, 1 more finger in the air, that's a p1. 3 total, sp2. Fingers stand for the p's. If I need 4 electron domains, sp4, it's 3 more fingers in the air. sp3 is 4 electron domains. Finger-thumb rules, oh my goodness, makes all this hybridization talk easy. sp3 hybridization, 4 electron groups. We just looked at that. If I have a central atom, that's carbon, sp3. 3 more fingers in the air. sp3 gives us 4 electron domains. And it truly is that simple. When I start looking at the combined molecular geometry, they start showing hybrid orbitals. What do they physically look like in terms of clouds? An S-shaped cloud is spherical. A P-shaped cloud is an hourglass. Combine these 2 pictures and we get a hybrid orbital. This represents 4 degenerate, which means of equal energy. sp3 creates what we used to have as an S, P1, P2, P3, or what we called PX, PY, PZ. But if I hybridize to create 4 degenerate of equal energy levels, originally an S and PX, PY, PZ, create equal energy levels, and we get this combined picture. So all a hybrid orbital means is that they are now degenerate, which means of equal energy. So back to our original thinking, if our energy level, S's are of lower energy than P's, we make them all equal. If an S originally is of lower energy, we promote the electrons. Notice they're between. An S is below, a P is above, where now the hybrid orbital lies directly between. It's more energy than an S, lower energy than a P. It's a hybrid of the 2. In an sp3 hybridized atom orbital diagram, another picture of the same idea. Originally, an unhybridized carbon atom would have 2 electrons in the S sublevel, 2 more in the p sublevel, leaving an empty energy level. Who wants an empty bedroom in the house? Let's let them spread out. These two remained the same. These two were hybridized. If all 4 create bonds, again, if the carbon atom fills all 4 of these to create 4 electron domains, it's said to be sp3 hybridized. We need 4 domains. Your thumb is an S, 3 more fingers, sp3. Can't make it any easier than the thumb finger rule. Draw the orbital diagram for the sp3 hybridization of each atom. Well, here's chlorine. 3s2, 3p5 would be its normal configuration. And again, if I place chlorine around a central atom, 1, 2, 3, 4, 5, 6, 7 valence electrons. Chlorine, with its 7 valence electrons, will create 4 bonds. sp3, 4 domains. This gets just very simple if I use finger-thumb rule. Here's oxygen with 4 domains. S2, 1, 2, 3, 4, 5, 6 total electrons in the outermost shell. It lives in group 6A. 2s2, 2p4, leaving 2 empty spots for bonding. If we create, instead of S and P, we create that tweener level, the hybrid orbital, all of equal energy, we create an sp3 orbital with 4 domains, sp3, a total of 4 fingers in the air, 1 being a thumb, sp3 hybridization. So according to the valence bond theory, bonding takes place between atoms when their atomic or hybrid orbitals interact. That's literally just an overlapping of orbitals to create a space to share electrons. To interact, the orbitals must be either aligned along the axis between the atoms or be parallel to each other and perpendicular to the interatomic axes. So, in other words, I can have them parallel or I can have them perpendicular. A methane molecule with sp3 hybridization. Here's carbon in the center, 1, 2, 3, 4 bondings. Methane is CH4. We would draw its molecular structure with 4 bonded pairs. 440 is its molecular geometry, tetrahedron. To get 4, we raise our thumb first for the S, 2, 3, 4 fingers to get 4 electron domains, sp3. The fingers are the P's, sp3 hybridization. Now in that, they're all single bonds. Ammonia with an sp3 hybridization, one of these would be simply a lone pair of electrons, 3 hydrogens bonded with a single bond back to the nitrogen. To get 4 electron domains, we get an sp3 hybridization. Back to talking about bonds and the way they align themselves in a geometric fashion. If we see a single bonds form are known as sigma bonds. They result when the interacting atomic orbital points along the axes connecting 2 bonding nuclei. S to S orbital overlapping is a sigma. A P to P orbital overlapping is a sigma bond. Hybrid to hybrid, hybrid to S, any type of single bond where a types of bond again, single bonds are known as sigma bonds. Any type of overlap, S to S, P to P, hybrid to hybrid, any other combination, the first is always a sigma bond. When the axes interact, connecting by just a simple overlap, it's known as a sigma. Pi bonds result when the bonding atomic orbitals are parallel to each other. So instead of pointing along the axes connecting, they're literally overlapping by a parallel connection, as in a double bond. So perpendicular to the axes connect to create a pi bond. The interaction between parallel bonds is not as strong as between orbitals at each other. sigma bonds are stronger than pi bonds. Let's show with an example what we're referring to. If I take a p orbital and overlap it with a p orbital, think about those two overlapping, we create a pi bond. And they're literally showing an envision of me trying to draw. Take this guy, and just put them together, overlapping. So parallel to parallel connect to create a pi bond. A sigma bond is end to end. Take these two, the same hourglass shaped P, but instead of overlapping as in like a figure 8 would overlap like this to create something along those pictures, end to end creates a sigma bond. All right, so I'm going to just represent, and this will just be a blank sheet of paper. Suppose I have a simple molecule like methane, CH4. Sigma bonds are single bonds. Carbon to hydrogen would be a sigma bond. Here's yet another, here's another, here's another. The way that these orbitals overlap is end to end. Hydrogen with its little spherical S-shaped cloud, carbon would be overlapping that with its P-shaped cloud. The P-shaped cloud creates a sigma bond end to end. Methane has 4 sigma bonds. Sigma is a Greek symbol. Carbon, let's do something like this. Formaldehyde. C double bond O, single bond to hydrogen. The first bond is always a sigma. Even in this double bond, the first is a sigma. The second bond would be a pi. Now just thinking what I just said, carbon overlaps end to end first. The orbitals that look like hourglasses will align end to end. The second will combine parallel to parallel, overlapping P-shaped clouds parallel in the same plane. Sigma bond here, the first in a double bond, always sigma, the second will be a pi. This structure has 3 sigma, 1 pi bond. If I have something like carbon monoxide, a triple bond. First one is always a sigma, the rest will be pi. This particular structure has 1 sigma and 2 pi bonds. I don't know why I wrote the word, 2 pi bonds. In multiple bonds, the first is a sigma, the rest will be pi. If you're asked to look at structures that are complex carbon chains, let me just kind of look at making one up here. We'll make those hydrogens. How about a triple bond to nitrogen here? Let's count the total number of sigma and pi. Every single bond is always a sigma. Every first bond of a multiple is a sigma. The rest are pi. So let's label. Here's sigma. First here is a sigma. Sigma. Again. I count 1, 2, 3, 4, 5, 6 sigma bonds in this structure. Again, sigma just simply means end-to-end overlap, very strong bond. Pi bonds occur when we have double or triple bonds. The first is always a sigma, the rest are pi. In the carbon to oxygen double bond, there's 1 pi bond, the other is a sigma. In the carbon to nitrogen bond, first is a sigma, then I see 2 pi bonds. 6 sigma, a total of 1, 2, 3 pi bonds in that particular structure. It's just describing the orientation in which bonds are formed by overlapping orbitals. Sigma bonds are end to end. Pi bonds are, if this is the plane, you're going to overlap those orbitals top and bottom, as in a p bond. So best I can I'm drawing, you know that's my forte. And this concludes the chapter 10, The Vesper theory being the big idea, hybridized orbitals with the thumb finger rule, and just counting sigma pi bonds are the three basic skills that